All right, so in this section, we're going to be looking at defining conics a new way using what's called its eccentricity. So we'll talk about what that means. And then we're also going to be classifying conics using coefficients, okay? So first, let's just review. We started off the unit talking about how we can get the different conic sections by intersecting a plane with a double napped cone, right? And the four that you see on the top of the screen here, those are the four that we've looked at so far. These are like the common conic sections: a parabola, an ellipse, a circle, and a hyperbola. But there are three other possibilities for the intersection between that plane and the cone. And I think, Eli, you might have asked about the one earlier when we first looked at this. But the three on the bottom, these are known as degenerate conic sections. And these are like special cases, all right? So if you have the plane intersecting at the vertices of the two cones where they connect, then your intersection with the plane is just going to be a single point, okay? Second situation, maybe you angle the plane in such a way that it intersects each half of the cone right on a slant. You would only have one intersection line. And then the third possibility is you could have the plane perpendicular to both bases of the cones. And if that were the case, you would have two intersection lines, two crossed lines that intersect at the vertices of the cone, okay? So those are known as degenerate conic sections, all right? And I want you to understand that all of the examples that we covered today, they would not apply to these special degenerate cases, all right? They're only going to apply to the four above, all right? So let's talk about eccentricity now. Let F, the focus, be a fixed point from a fixed line D, the directrix. Let P be a point in the plane of both D and F. And let PD be the distance from point P to that directrix line D, okay? We're going to consider the set of points for which the ratio of the distance from P to D is with the distance from P to F, okay? That ratio of PF to PD is a constant, E, and we're going to call E the eccentricity of the conic section, okay? So this is a new way of looking at the conics, a different way of defining them, all right? And so far, we've only looked at one conic, the parabola, that has a directrix with it, right? In this approach, in this definition, every single one of the conics has a directrix associated with it, okay? Now, if you find the eccentricity, that value E, to be a number between 0 and 1, if that ratio is between 0 and 1, then you are dealing with an ellipse. Okay. If that ratio is exactly 1, you're going to have a parabola. If the eccentricity is greater than 1, you will get a hyperbola. And on the off chance you get the eccentricity to be 0, you are going to get a circle. And the reason for that is a circle doesn't have a focus point, so the distance from any point on the circle to the focus would be considered 0, making the ratio for the eccentricity 0, okay? So I kind of have this pictured over here for us. We've got, the focus point, we have the directrix line, and then we just got a random point P in the plane. So what we're doing is we're trying to find these two distances and come up with that ratio. It's always PF to PD, okay? Now I'm going to illustrate each of these scenarios dynamically. Okay, so we'll look at the ellipse eccentricity first. Okay. So notice here, I've got a point A that's on the ellipse. I have a focus point, and then I have a point B that's on my directrix line. The distance from A to the focus, they're showing me, is 2.5. And the distance from point A to the directrix line at point B is 3.58. The ratio of those two distances would be 2.5 to 3.58. That'll simplify to 0.7, which is smaller than 1. Okay? Now notice it doesn't matter which point I pick on the ellipse, that eccentricity remains the same, 0.7. Okay? Now, I'm going to increase the value of,
How do you find a directrix line for an ellipse?
It'll be given to you.
Okay.
It'll be given to you. Yeah. Okay, so now I'm going to increase the eccentricity value. And notice I'm still in ellipse until I get to E being exactly 1. Right there. Okay, so this would be a parabola. And the parabola is the one conic we've looked at already that has a directrix associated with it. And we said the distance from any point on the parabola to the directrix should be the same as the distance from that point to the focus, right? Well, think, if those two distances are equal to each other, what's the ratio of them going to be? It's going to be exactly 1, right? Okay, now, if I increase the eccentricity beyond 1, now's where I start to get the hyperbola, and you can't really tell until I get it bigger. You see the lower half of the hyperbola showing up there, right? Okay, look at the distances now. From A to the focus, the distance is 3.11. From A to the directrix at point B is 1.3. The ratio of 3.11 to 1.3 is going to be something larger than 1, 2.4 in this case. Okay? All right, so let's go to example 1 here. It says, let F be your focus at the point 0, 6, and your directrix be x equals 3. We want an equation of the set of points P for which PF divided by PD equals 2. So they're giving me the ratio of these distances. So that number E, that is your eccentricity here. Okay, I'm going to say that we're working with a hyperbola because E equals 2, and that is greater than 0. Okay, so let's try to sketch this. All right, there's the focus point I've been given at 0, 6. Here's the directrix I've been given. All right, and I'm supposed to have this random point P somewhere in the same plane as these two, right? Well, P could be here, but also maybe it could be over on the other side of the directrix. Okay, so I'm going to have to make this work for all situations, all right? So if PF over PD equals 2, that's no different than saying 2 times PD equals PF, right? Okay, now I want to come up with an expression or a formula to represent the distance from point P to this directrix line D, right? So I want this distance here. Well, as is with point P to the right of the directrix, I could say I could find that length by simply doing x subtracted by 3. The x coordinate of point P subtracted by the x value from the directrix of 3. Okay, but what if I'm over here? What if point P were there? Then wouldn't the distance be considered 3 minus x? Okay, so I need to make this work for either possibility. okay? Sometimes when I perform that calculation of x minus 3 or 3 minus x, I might end up with a negative value, right? So what I'm going to do to account for that is just use some absolute value. Okay? All right, now distance from point P to point F, that distance right there or that distance right there is just utilizing the distance formula. It would be the square root of x squared plus y minus 6 squared. Now what I'm going to do is manipulate this and try to simplify it down to an equation of a hyperbola in conic form. All right, so I'm going to square both sides. Okay, now when I do that, 2 becomes 4, and then the absolute value of the x minus 3, you can effectively ignore the absolute value when you go to square it, right? Because it doesn't matter if x minus 3 is positive or negative. When I square that, it's going to turn positive regardless. Okay, and then over here, the radical goes away. And then how about I expand out the binomial? I'll expand this binomial out now. Distribute the 4 through 4x squared minus 24x plus 36. Okay, those are going to cancel out. And then I think I want to move everything to one side here. So let's make this 3x squared minus 24x minus y squared plus 12y equals 0. I'm going to factor a 3 out from the first two terms that have x in them. Set up a blank for completing the square. What should I factor out from the y terms? Anything? Yeah, you want to pull a negative 1 out. So that's going to make this a minus 12y. And over here we have 0, and then we have to balance things out with 2 more blanks. Complete the square on x. This should be a 16. Half of negative 8 is negative 4. Square it 16. On the other side of the equation, I should put in a 48, right? 3 times 16. Complete the square on y. I think I need a 36 there. On the other side, what do I need? Negative 36. Good. Factor. So you get a 12 there. And then we'll divide the 12 out. So we'll end up with x minus 4 squared over 4 subtracted by y minus 6 squared over 12 is equal to 1. And look at that. Is that not an equation of a hyperbola in conic form? All right, now I'm going to check this if I have the extra time. So I can tell you the center here is 4, 6. Which way does this hyperbola open, left and right or up and down? Left and right. Okay, and my c squared value will equal a squared plus b squared. So that's going to give me 16, making C 4. And the reason I'm finding C here, C gives me my foci, right? Well, I was given one of the foci of this hyperbola from the get-go. So if we're opening left and right, I will add and subtract 4 from the x-coordinate of the center. 4 plus or minus 4, 6. So look what that gives me. 0, 6, and 8, 6. Was that one of the focus points I was provided at the beginning? 0, 6. There's a nice check. Questions there? All right, example 2. Essentially the same question, except here the directrix is a horizontal line, y equals 3, and the ratio of P to F, of PF to PD is now 1/2. Okay, this would be an ellipse then, right? Because the 1/2 is your eccentricity, and that is less than 1. All right, so sketch it out again. Right there's the focus. There's your directrix. Okay, now we could maybe have point P up here. Maybe it's down here though, we don't know. If the ratio of PF to PD is equal to 1/2, that would be no different than 2 times PF equals PD, right? So carry the 2 down. The distance from point P to F would be the square root of x squared plus y minus 6 squared again. Okay, now what's the distance from P to D? Well, here it would be y subtracted by 3, bigger y value minus smaller y value. Or here it would be 3 minus y, right? Okay, well, we're just going to account for it. We got to make this work in all situations for positive or negative results. So I'm just going to use the absolute value of y minus 3. Okay, now I'm going to square both sides. The 2 is going to become a 4. The radical will go away. Carry the x squared down and then expand the binomial. Y squared minus 12y plus 36. Over here, the absolute value becomes unimportant if you're now squaring it, right? Let's distribute the 4. Expand the binomial. Okay, I'm going to move everything to one side except for the constants. Okay, so let's see, I got 4x squared. If I subtract y squared over, I'm going to get a 3y squared. Add 6y over, I'll get a negative 42y. Subtract 144 over, 9 minus that would be negative 135. Okay, nothing to complete the square on for x because I don't have a linear term. So just carry that down. For y, I'm going to pull a 3 out. What number completes the square on y?
$49.
49. Okay, 3 times 49 means the other side should be 147. Factor. Equals 12. Divide that 12 out. So I'll end up with x squared over 3 plus y minus 7 squared over 4 equals 1. And that is the equation of an ellipse, is it not? And I could do a similar check there. I could find the center, 0, 7. I could get my c value, which in this case would just be a 1. And from the center, if I just move 1 up and 1 down, that'll get me back to my focus, one of which will be 0, 6. Questions there? All right. Okay, now let's take this another direction, all right? Consider the equation ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. As long as a, b, and c are not all 0, then the graphs of these are going to represent a conic. And this would be if we're not working with those degenerate situations. Okay? So if a, b, and c are all not equal to 0 and the graphs are not degenerate, then we could use the discriminant to help us determine what type of conic we're working with. Okay? Now, one thing I want to draw your attention to here is this term. None of our equations so far have had a term that's got both x and y in it. Okay? So if this is the case, and b does not equal 0, then what that means, it means the conic section has been rotated, which we haven't really looked at that situation yet. Maybe something we'll visit much later on in the course. I don't know. We'll see. But by rotated, I mean rotating it to where the axes are not horizontal or vertical. Okay? Everything we've worked up to this point, b has been 0. All right? Okay, so the discriminant of this equation would be b squared minus 4ac. Okay? That graph is going to be a circle or an ellipse if b squared minus 4ac is less than 0. Okay? Now, it'll be a circle more specifically when b is 0 and a and c are the same. And notice a is the coefficient on the squared term and c is the coefficient on a is the coefficient on the squared x term and c is the coefficient on the y squared term. Okay? If that discriminant is 0, you'll get a parabola. And if that discriminant is greater than 0, that's where you'll get the hyperbola. Okay, those are rules you're going to need to know for the upcoming test. All right, so final example. Identify the graph of each equation using the discriminant. Okay, I put the form up there in red for us to reference. Okay, so looking at the first equation on the left there, I would say A is 1 for here. B is negative 2, the coefficient of the xy term, and C is 3. So B squared minus 4AC would equal negative 2 squared minus 4 times 1 times 3. That's going to be 4 minus 12, which is negative 8. Okay, negative 8 is less than 0, so we're either working with a circle or an ellipse. Okay, well, A does not equal C, and B is not 0 in this case. So we are not a circle. This is an ellipse. Okay, final example. A is 1 again. B is negative 4. C is 1. B squared minus 4AC would be negative 4 squared minus 4 times 1 times 1. That's 16 minus 4, or 12. 12 is greater than 0, so this is a hyperbola.